Here in this video, we're going to look at the integral of the natural log function. And here's the formula. It says if we let u be a differentiable function of x, so once again here, u is not just a variable, u is a function of x, then it says the integral of 1 over u du, so if we can get our integrand to fit this form, 1 over u du, then the integral is simply the natural log of the absolute value of u, and of course plus our constant c. Well, if we recall, when we looked at the derivative of y equals the natural log of u, then y prime, the derivative here, we said that would be simply the derivative of u, which would be du over u. Well, because these are inverses of each other, if we were to integrate this, it would make sense that we want to go back up to the natural log of u. And that's exactly what we have over here with our integral. We have 1 over u du, and we could think of this as the integral of du over u. And if we have this integral here, so 1 over u du is the same thing as the integral of du over u, then that's simply going to be the natural log of the absolute value of u plus c. So in a lot of cases, we think of this as du over u, and then we know that we have the integral here that's going to equal the natural log. Now, why do we need to do this? Well, if I give you the following example, if we have the integral of 2x to the negative 1 dx, how do we integrate this? Well, looks pretty easy at first. You would say, well, we would write down 2x and we increase the exponent to by 1. So negative 1 plus 1 is 0. And we divide by 0. But what happens? Well, we notice here we cannot divide by 0. So that is not going to work at all. So therefore, we have to have a rule that's going to fit this. And it happens to be our natural log. So if we have the integral of 2x negative 1 dx, then we can think of rewriting this as 2 over x to the first dx. And again, this 2 is just a constant multiplier, so we can take this 2 and pull it out front. So it'd be 2 times the integral of 1 over x dx. Okay, or we could actually write this as the integral, 2 times the integral rather, of dx over x. Okay, that's a different way of writing it. And if we look at it this way, then I can say, well, hey, if I let u equal the denominator, if u is equal to this function here, x, if u is equal to x, and if I take the derivative, here is our u, and if I take the derivative of this thing, then du is equal to 1 dx. You could write 1 dx or just simply dx. Well, here we have our du. So we have du over u. And of course, if we have du over u, then that means we have our 2 out front. Du over u fits our integral, so that means this would be the natural log of u, okay, the natural log of the absolute value of u. So in this case, it would be the natural log of the absolute value of x plus c. Okay, so really the hardest part is just trying to get your integrand for your integral here to fit this form of du over u. Once we have this form, the integral is very straightforward. All right, let's try another example. Here we have a definite integral. We have limits here. So we're looking at the integral of x over x squared plus 1, integrated from 0 to 3. Well, once again, if we think about our formula, usually here with the formula, if we find this form, we're trying to let u equal the denominator, and then hopefully our numerator will be the derivative. So if we look at this one, we could say, well, if we let u equal the denominator, which is x squared plus 1, then if we take the derivative, du would simply be 2x dx. And we look over here, we actually have x squared plus 1, so all of this is u. And we have the x and the dx for the du, but what are we missing? We're missing the 2. Well, just like we've done in the past when we were looking at integrals before, we can simply multiply a constant on the inside and then by 1/2 out front. So then we could think of this as 1/2 the integral of 0 to 3, and we actually have the form here 2x dx. And again, I like to kind of group this as 1 over x squared plus 1. And then we know that 2x dx, all of this is our du. So we know when we integrate this whole 2x dx here, all of this is going to disappear. So here we simply have 1 over u. Well, if we have 2x dx, which is our du, so we have du over u, so that fits our formula. So we simply bring down the 1/2, and we're going to multiply that by the natural log of the absolute value of u. Well, u is x squared plus 1, so we get x squared plus 1, and now this time we don't have plus c because we have our limits of 0 to 3. So now remember, if we're plugging in the limits, we start with the upper limit. So we're going to plug 3 in. And if we do that, now one thing I do want to point out before I do this, notice here we took the absolute value of x squared plus 1. And you may see this happen. Remember, why did we put this in absolute value? We put this in absolute value because we know that this quantity x squared plus 1 must be positive in order to take the natural log. Well, if you think about this here, if we plug a number in for x and we square it, that's always going to be positive. And if we add 1 to it, that's still going to be positive. So sometimes you'll see that we can then leave out the absolute value, and we could just use parentheses here because there's no way for x squared plus 1 to ever be negative. So be aware that you'll see some simplification of this type from time to time if it's impossible for this to be negative. So now we can plug in the upper limit. That means we would end up with the 3 going in, so that's 3 squared is 9 plus 1 is 10, so we get the natural log of 10 minus, and we plug in the 0, we would have minus the natural log of 1. And sometimes you may actually see, if you look at this on a quiz or example out of a textbook, and sometimes they leave the answer in your book like this, instead of actually taking the natural log, they leave this more in an exact answer. And of course you can put this in the calculator and you would come up with a decimal of approximately 1.151. Okay? So again, we're trying to fit the form of du over u in order to have our natural log. Alright, so here we have another example, and maybe at this point you want to pause the video and see if you can try to solve this one on your own. And here we have the integral of x over the square root of 9 minus x squared. What do you think we're going to let u equal? Now, if we let u equal the entire denominator, then we're looking at 9 minus x squared raised to the square root be raised to the 1/2. And if we take the derivative, we're going to end up with the chain rule. So that's 1/2 times 9 minus x squared, and we decrease that to a negative 1/2. And then we take the derivative of the inside, which is a negative 2x, and that's nowhere to be found in our integral. So this looks a lot more complicated when we do this. So it's probably a good chance that we need to go back and rethink what we want to let u equal. And maybe it's a better thought to not to let u equal the whole denominator, but maybe what's underneath the square root here, and let u equal 9 minus x squared. And then if we take the derivative, we would simply have a negative 2x dx. Now, if you look closely, we have a x dx. The only thing that we're missing is the negative 2. So we can certainly multiply here by a negative 2 and a negative 1/2 out front. So now what form do we have? Now look carefully here. Do we have du over u? And at first glance you say, of course we do. But if you look very closely, you're going to notice that on the bottom we had 9 minus x squared. That is our u. And we have a negative 2x dx on top, which is the du. Well, if I really rewrite this, what we really have here is negative 1/2 multiplied by the integral of, we have du over the square root of u. So notice here, this is not du over u. So for our integral, we're looking for du over u if this is going to be equal to our natural log. So here we have du over the square root of u. Well, this actually turns out to be one of the problems we've done in the past. This is just what we call a basic u substitution. So we could write this as the square root of u, that's u to the 1/2. So if we move it to the top, it becomes u to the negative 1/2 du. And this is just a straightforward integration. So we have our negative 1/2. And if we take u to the negative 1/2, that would be u, if we increase that, that becomes to the positive 1/2, and we divide by 1/2. So we're going to multiply by the reciprocal, which would be 2 over 1, or simply 2. And we'll notice here that the 2 and the 1/2 here, they would cancel out. And we have our negative out front, so we can bring down the negative. And then this is u to the 1/2. Well, our u is 9 minus x squared, so we can plug that in. So we have 9 minus x squared, and all of this is still raised to the 1/2 power, or you can write it as the square root, plus our constant. And there's our derivative. So be aware that don't always try to force everything now to du over u. There's a habit that students have is once they learn a new technique, they think everything's going to fit that technique from here on out. Well, all of the rules we learned in the past still apply. So that doesn't mean that all the problems that we look at now are going to simply be du over u, where they're going to be equal to the natural log. Okay, here's our next example. We have the integral of x times x plus 2 all over x cubed plus 3x squared minus 4 dx. So what do you think you want to try? Well, you might say, well, let's try to let u equal the denominator, x cubed plus 3x squared minus 4. And if we take the derivative here, we have 3x squared plus 6x dx. All right, so now, do we have the du? Well, if we look at the top, we have x times x plus 2. This is going to be what? X times x is x squared plus 2x. So let me go ahead and rewrite this. We would actually have on top x squared plus 2x. And what do we notice here about the numerator? Well, the numerator almost looks like our du. We have the x squared and the 2x, but it looks like our du here, we need a factor of 3. So it looks like all we need to do is multiply the numerator by 3, and then of course a 1/3 out front. So therefore, if we do that, we're going to end up with, we have the 1/3 out front, and we would certainly have 3x squared plus 6x over x cubed plus 3x squared minus 4. And at this point, we certainly have our 3x squared plus 6x dx. This is our du over u. So that means we would have then 1/3 the natural log of the absolute value of x cubed plus 3x squared minus 4. And there's our derivative. Now, usually you can see that you're going to have du over u if your numerator, if you look at the exponents and compare them, if the exponent in the denominator is 1 larger than the exponent in the numerator, we know that it's a good chance you're going to have du over u, because once we take the derivative of the denominator, your exponents are going to decrease by 1. So that means your exponents in the numerator must be one lower than the exponents in the denominator. So now here we have our next example, and with making that statement about the exponents, what do we notice here about this example? Well, we have a larger exponent in the numerator than we do in the denominator. So of course we would first say, well, wait a second, if we let u equal the denominator, then the derivative is just going to be 1 dx. And clearly that's not going to work. Now here's a technique, and we've mentioned this a little bit in the past here. If the exponent in the numerator is equal or greater than the exponent in the denominator, then this leads us to the opportunity of using long division. So we can take and divide the denominator into the numerator. So we would have x cubed. Now keep in mind we need to write these in descending order, so I'm going to put in a placeholder of 0x squared minus 6x minus 20. So then if we divide, hopefully you remember how to do this. What do we multiply x by to get x cubed? Well, that means we need an x squared. So x squared times x is x cubed. X squared times 5 is 5x squared. And then, of course, at this point, we need to subtract, so we're going to change our signs. And once we change the signs, then the x cubes cancel, and we have 0x squared minus 5x squared. So that's a negative 5x squared. And just like regular division, we bring down the negative 6x, and we repeat the process again. What do we need to multiply the x here out front by to get negative 5x squared? So we need to multiply by a negative 5x. So negative 5x and x is a negative 5x squared. Negative 5x and 5 is a negative 25x. So once again, we're subtracting, so we're going to change our signs. And now the 5x squares cancel out. We have a negative 6x plus 25x, which would be 19x. And then we bring down our next term, which is negative 20. Now what do we multiply the x out front by to get 19x? And of course that would be 19. So 19x. And then 19 times 5 is 95. Once again, we changed our signs, and we have a negative 20 minus 95, which is a negative 115. So here, the negative 115 is our remainder, so we would go up here and we could write minus 115 over x plus 5. Okay, then that's going to be our new integral here. Then we could write this, and you could view this really as each term here. We have 1, 2, 3, 4 terms, so we could think of this as 4 separate integrals. And I will write that out that way. You don't have to necessarily write it this way, but you'd have the integral of x squared dx minus the integral of 5x dx plus the integral of 19 dx minus the integral of 115 over x plus 5 dx. Now I just wrote this out each one separately. You could certainly just write this as the integral of x squared minus 5x plus 19 minus 115 over x plus 5 dx. You could think of it this way, and then you would just certainly integrate each term individually. But here I wanted to go ahead and just set this up to realize that we're really thinking this as 4 separate integral problems. And if we look at the first 3 here, they're very basic. X squared dx, that's just simply going to be x cubed over 3 minus, and then we have 5x, so that's going to be simply 5x squared over 2. And then the 19, we're just going to plug an x in, so that's 19x. All right, then we have this last integral, and I'm going to go ahead and rewrite this, and I'm going to bring it down. The 115 is a constant, so I'm going to pull the 115 out front, and we're really left with 1 over x plus 5 dx. So hopefully now you will notice that if we let u equal the denominator, x plus 5, and we take the derivative, well, the derivative of x is just going to be 1, so we just have dx. So here we have our du, x plus 5 is our u, so of course now we have du over u, so we would simply then have, we have our x cubed over 3 minus 5x squared over 2, 19x, minus 115. And now that we have this du over u, that's going to be the natural log of u, which is simply x plus 5. So here we have our derivative. And a lot of times this is going to happen. If you perform the long division here to find the integral, usually the first several terms here on top are going to be very straightforward because you just have a nice polynomial type function, and your remainder typically is going to be able to be integrated by finding du over u using the natural log. So keep in mind here, the formula we're looking for is du over u, and that's going to give you the natural log of u. But once again, please be careful and try not to fit everything to fit this form, because sometimes you will just have a basic u substitution.